simpler to, well, let me not speak too soon. I think they made it simpler to live stream on YouTube. So we normally
Hmm.
record and live
Hmm.
stream on YouTube,
Okay.
and it's working. Okay.
Okay.
Or seems to be working. Let me see. Let's see. Oh, yeah, absolutely working. Ha ha
Good.
ha.
Yeah.
Okay. So then that way I don't have to put the Zoom link on social
Yeah.
media because that just invites problems.
So where are you located now? It's Johannesburg.
So I am normally located in just outside of Washington, D.C.,
Ah, okay.
but
Okay.
the
So
AFLS
long
office
guess.
is in Johannesburg, and
Okay.
Trevor Sewell is in Cape Town, and
Hmm.
Chart Kruger. So the three of us actually we organize these things.
Hmm. Okay.
So they are in South Africa, but I'm in the United States.
Okay. Okay.
Oh,
So what time is it now in South Africa?
so in South Africa, it is 4 p.m.
Okay.
It's
Okay.
10 a.m. in Washington, D.C.
Okay. Let's see.
Uh,
4
Trevor, I'm going to make you a co-host because there are electricians working in my building. So if they do something bad,
Okay.
I hope that if my machine goes out, the other co-hosts can continue the meeting.
Okay. Okay, that's fine.
But if and I joined the meeting using my phone as well. So if they tripped a circuit breaker not too long ago, but luckily it was on a circuit that my machine is not on. But I don't want to find out the hard way what if things go poorly. Okay, so I'm gonna post this to here. So we usually start like 5 minutes after to give people
All right. That's okay.
time to get themselves together.
Yeah. Yeah, actually it's 11 p.m. here.
Oh
So
wow. Thank you for
I'm not
staying up
going
so late
no,
to
I'm
do
not
this.
going anywhere. So
He's- I think Zoom is so great because we can connect
Yeah.
around the world instantaneously almost. I mean, this is like awesome. Mm. Oh, I guess I'm supposed to be doing an introduction.
Thank you.
Um,
Yep.
okay. I'll just make it really short
Yes.
so people can read the. Okay. Um, okay, we'll start in 2 minutes.
Okay.
And how do I pronounce the last name correctly? It's
Who?
who?
Just
Okay,
like who's first, who's second.
gotcha. Okay, thank you.
Yeah.
Okay, folks, I have 5 minutes after, so
Mhm.
I'll start with a quick introduction of the speaker. Is Professor who is a fellow of the Chinese Physics Society and the CEO of the Synapse Project. The Synapse Project, as we will learn, is a consortium to map the entire brain, it involves synchrotron radiation and also a lot of computing. If you got the announcement for this talk, you have his bio. So I will just invite you to read that. And then we can get straight away to Professor Hu. So thank you for coming today.
Yes. Okay. Thank you for the introductions. I believe this is the second time I'm speaking to this seminar, and then I just find out that actually the last time is almost already 2 years before. Okay. So anyway, today's I am Yu Kwang Hu. Actually I made myself because we don't have such a position. But after consulting with the members of this consortium, um, they decided to give me this title so that when I was giving the talk, I could represent on behalf of the Synapse Consortium and all the other members. My own position research is in Academia Sinica, which is sort of like the Academy of Science in Taiwan, and then my Institute of Physics department, Institute of Physics. So before I start my talk, actually I was just asked to see how we can organize this conversations or this meeting more. And then it just happened that in the next month there's a meeting in Sanya, China. So I know it'll be very difficult for you to make a plan right now, but just in case you're nearby, or I believe they offer some online access. So this meeting, as you can see, is organized by two academicians of the Chinese Academy of Science, Professor Mu Mingpu and then Professor Qiming Lo. And Mu Mingpu is a well-known neurobiologist. He also happened to fund or funded the Chinese Brain Project several years ago. And then this Brain Project is about to finish its first phase, started from 2020, I believe. And then now they shift the focus, another shift the focus. They actually put the connectome mapping as one of the key target for the Chinese Brain Project. And then Professor Pu also has a very good intention to make this international program. So that's why he asked us to be working with them. So in these meetings, we will have a small sort of satellite meeting, and just to mention, just to discuss all the issue we are facing now in the computation. Okay, and then this so this is the information. So let's see if you are interested to join the meeting. Okay, and then I will start with my talk because this is, I believe that the audiences are more related to synchrotron radiation. So I would start by briefly introduce a few, I believe, which is the breakthroughs in the X-ray imaging, which make what we're doing or plan to do possible. Of course, the first one is the phase contrast in X-ray imaging. And this, I think, is so well known. It's from its first realization or in with a synchrotron light in the early 1990s. It's already 20 to 30 years. So I think it's pretty well known. It's implemented almost in every synchrotron. So I will not spend too much time on this. And then the second breakthroughs, I believe, which are also very relevant to what we're doing, is the high resolution. So specifically, that we are able to use X-ray imaging to now reaching nanoscale resolution. Okay, and then the third, which is will become probably important in the future after we complete the first phase of our task of mapping the brain, is then try to study image more information. And then this is the elemental contrast. Okay. And then actually the most important features of X-ray imaging, which allowed us to take on this grand challenge of mapping the brain of the human brain, is actually its inherent or the very high speed due to the development of the 20 years of development and in X-ray 3D imaging. Okay, I would also show a few slides just to say what we mean by each of these breakthrough. The nanoscale resolution in 3D, which is, okay, one of the example which I personally involved is my research program since 2005. So is to develop the X-ray microscopy, which is the configuration is very similar to a TEM, transmission electron microscope, and that's why we call it a transmission X-ray microscopy. And then it is a full field imaging technique with we're using an objective lens, which to magnify the X-ray image passing through the sample, and then using this X-ray optics to magnify the X-ray image, and then going through this and then project to the right side, and then captured by a visible light, a CCD, which has scintillating screen in front. So basically, this objective is just like our normal magnification lens, and then we magnify this X-ray image. But then X-ray images is not easily detected by a high resolution detector. So in front of the CCD, we have a conversion device, which is typically a single crystal scintillators, which can convert the X-ray imaging to X-ray images to visible light image, and then captured by the CCD with a visible light objective. So the key optics here is this zone plate or phase zone plate. And I will show, and then our development since 2005 is to make this zone plate. So over 2 years, I think in 2007, we achieved already a 20 nanometer width zone plate. And this zone plate is made of gold, as shown of some of the SEM images here. And the best performance zone plate optics we made is with an outermost zone of 20 nanometers. And then with the thickness of this gold structure of 450 nanometers of half micron. Okay. And then we also make other thicker structure, but because this fabrication approach, mainly the limitation mainly is its aspect ratio. So if we want to increase the thickness of the gold structures to something like close to a micron, then the outermost zone we can write and develop then become also limited. So the best one we made is like a 40 nanometers. And so, but with a thicker gold structure that you enhance, you increase the efficiency of the zone plate. So you'll be able to capture more light and then forming a brighter image with this resolution, which is comparable to the outermost zone width. Okay, so as you can see here, and then some of the zone plate we make, and then using this type of zone plate, and then we make a test with X-ray, this transmission X-ray microscope, such as the images shows here. The one on the top right corner, which is actually done by SEM, and then the other two are actually X-ray image, and then transmission TXM images. And you can see we made this gold pattern, which with finest inner zone features about 20 nanometer pitch. So by looking this X-ray image, then do a very simple, say, power analysis, then we can find out that the resolution is actually at the order of around the 15 nanometers. So, and then compare this SEM image with this TXM image below, you can see actually the image, the quality is quite comparable. And then what we can resolve is actually similar to what the SEM does. But if you look carefully, some of the feature that you can see actually is not uniform. So these are probably due to that when we grow this structure, grow these test pattern, the technology is almost identical as we grown the zone plate, phase zone plate. So this, when you grow, you make the electron beam patterning, define the pattern, and then you etch away the photoresist, and you use electro deposition to deposit the gold from ground up. And this process cannot guarantee you'll have a very uniform gold structure. So, and then I think while we see these variations of the the grayscale in this TSM image actually does reflect the density variation of the gold we deposit, and that it has become one of the key one of the reason that the efficiency of the zone plate optics cannot achieve approaching this theoretical value. But nevertheless, we can still do pretty good with this 20 nanometer outermost width zone plate with say half a 450 nanometer thickness. And then to image, for example, these are another type of test pattern we made for these type of tests. And then on the very left, it is a 25 nanometer pitch. On the middle is 20 nanometer, and on the right is 15 nanometer. And then these are the X-ray images. And then if you make a very simple line scan, then you can find out the modulation is reasonably well, still at the 15 nanometer. This is another proof that we are able to achieve 15 nanometer resolution. This was done actually, you see, published in the 2012, but the data was actually collected already several years ago before this. So it has been now more than 15 years since we have achieved this resolution. But as far as we know, this is still, if it is not the best, it's one of the best resolution that ever achieved with X-ray microscopy with a full field imaging approach. And using this, we can look at very simple biology sample with a contrast. Okay, like this is given by the nanoparticle we feed to the culture, and so the cell do the endocytosis uptake and take this nanoparticle into the cell, and then we can image with our X-ray microscope. And same on the right. Okay, and you can see this structure of the cell was actually cultured on a flat surface. So you cannot you can see it's on one side is on the covered glass, for example. And so it's 3D enough, but not very impressive as you would like to see from. And then the other breakthrough I was talking about is X-ray does give you elemental sensitivity, even in many cases can give you chemistry, chemical contrast. This is one example we did with published also more than a decade ago, is looking at this material. And then by using the photon energy at the above and below the nickel K edge, we can very easily, with very good contrast, to identify where, for instance, the nickel is. Okay, and then these the top images are the projection image, and then the bottom two, C and D, is actually after the tomography reconstruction. So it's a 3D picture. It's a projection. It's a snapshots of a 3D models, and we can see very clearly where the nickel is distributed. Okay, and then the other subject we study using the X-ray microscope, and also very almost also decade ago, is to study the angiogenesis. I mentioned this work is because that actually is how I was interested in using X-ray to look at brains. So this work was done by a collaboration with my colleague, my collaborator in University of Bordeaux, and then also the other medical institution. And then the objective is you want to look at the angiogenesis vessel, and then the target we choose is glioma, cancer tumor in the brain. Okay, so this is at that early example that we are looking at this is a normal mouse, and then with the perfusions of the gold nanoparticle that we self-synthesized and then injected through the artery, and then it was distributed to all the blood vessel, and then we take an X-ray microscopy, a tomography image. So, and then you can see this is not particularly dense because we set a contrast so that Otherwise, we probably would not see anything. So these contrast was set was high so that you only showed so the major vessels. But the point of this set of data is actually we're taking this brain without sectioning. So this is a mouse brain. We're taking this brain as a whole, and then using still very good resolution to image it together. And then that was actually a showcase of the power of X-ray imaging, because this was not done with a particular high energy, for instance, the 12 keV photons, and then it's already able to look through the whole brain without with a pretty uniform quality through the whole volume. Okay. And then using this technique, we're looking at the scientific interests. We want to look at the angiogenic vessels, as shown in these pictures. So these big clusters of vessels are the small, tiny, fine vessels, which is developed due to the growth of the cancer. So this actually coincide very well the size or the location of the tumor. So this 4 images actually was taken with a different stage of the cancer we inoculate, the cancer cell we inoculate to the brain, and you can see the scale was from 3 millimeter to 100 micron. So when we do this, we are actually quite surprised. Actually, in this very small tumor, which is quite small, that normally the other technique would not able to see it unless you sectioning and then be lucky enough to find it. But with X-ray, it's quite clear because of the gold nanoparticle contrast. And after this, you can see it's a very small. And then this actually help us to challenge the notions of the hypoxia, the reasons for the angiogenic vessel growth. I will not discuss too much more about that, but this is actually show the value of doing this whole brain image with a very high resolution. So these are some specific example. And then we have done actually in this work, we have done probably sacrifice 1 or 200 mice, and then with very different type of glioma tumor or cancer, for instance, the diffuse type, and then we are able to locate all the vessel which has been modified by these cancer cells or cancer. And then the solid one is like this. You have 3 big blobs of a tumor angiogenic vessels indicated actually here, for example, there are 3 separate tumor volume. And then with a very high, with the TSM, we are using this, I think the resolution is probably about 25 nanometer here. And then we can look at these are projection image or one slice of tissue that was, we can identify, for example, in the middle, this is a blood vessel through this tissue. And then with all these black spots are the red blood cell. And then if we do a tomography of a vessel like this, you can see like this. Okay, this vessel, the diameter is only 10 micron. So it's qualified probably the smallest vessel that you can see that there's still red blood cell here within the, and then these gold colored things are the gold nanoparticle we also injected to the bloodstream. And then the work of this work is we want to find if this particle can be leaked out of the vessel, which as we knew that, okay, the angiogenic vessel is very porous. And so that's actually one of the basis of nanomedicine is that we send drugs carried by a nanoparticle, then there's a very good chance that it can leak out through these angiogenic vessel, and which to achieve its therapeutic purposes to kill the cancer cell or reduce the tumor. Okay, so and then our study here we then concluded what we can do and what we can study. Mostly is that we thought, okay, well, when we look at the animal, this experimental animal, that we can learn a lot of what people use this experimental animal for. But unfortunately, this kind of imaging that we knew that at the time that we're not able to use apply to the medical imaging for clinical purpose or something, because the radiation dose is actually too high, which is associated with our increase of the resolution. So it's and then but then we were asking, okay, if we can image these blood vessels easily with the contrast agent, and then can we image neurons, and then can we image blood and neuron, a blood vessel and neuron together? And then, of course, we said we don't want to be challenged and say, oh, can you look at the human or live animal and so on? So it's not. So the work is done completed on sacrificed animals. Okay. So, for example, that very recently, the work I just showed you was done probably 10 years ago. And then 10 years later, we come back to this same problem, same subject is we want to image the blood vessel. And this time we have an idea, we have the intention to create a map, okay, which it just happened that we were told that actually non-human primates blood vessel was not completed and mapped, okay. And then the reason, of course, is because of compared to mouse, the brain size is 10 times bigger and so on. And then also it's the animal ethic and so on. Is make it more difficult to do. Okay, so this is the result we get. Okay, we're just looking at one particular part and then zoom in and then zoom in again. You can see that with this we can identify very small vessel, which is of order of 5 micron. So that means our perfusion method is very effective. It can go through actually from the artery all the way down to the very small capillaries. So you can see this filling, okay? And then if we magnify that, we can see the diameter is roughly, and then instead of showing just a point, which could be noise, so we show this is actually part of a vessel. And this is not complete because we cut it thin just to show this, because if we show the whole 3 volume, we probably cannot see anything without remove. And the whole brain looking looks like this. Okay, so all these things is with the vessel we perfuse with our nanoparticle contrast agent. And then this image, one of the important thing is we take this image without cutting the brain. The whole brain was put it on the X-ray, and then we achieve still very high resolution by patching the image and do a very large projection reconstruction. So there, okay, so this is, and then this is another example to show actually the density, and then we indeed can can reach the very small vessels. And so this is our claim, compared to other technique, for example, MRI, and there's no way that MRI can image a vessel with the order of tens of microns, because the resolution of MRI is hundreds of microns, if not millimeter. So MRI is very effective to study the function, the flow, and the perfusion, and these kind of things. But they did not have the resolution. So in terms of determining the structure, because we know the blood vessel, the smallest blood vessel is about 5 micron, because you need to be thick and large enough to allow the red blood cell to flow through. So once we detect this the vessel of a few micron, we knew that we're reaching the smallest vessel. And then we can claim, because all the vessels are connected, when you perfuse all these particles over one point, it can go through everywhere. And then if we image that, then we actually effectively delineate the whole vascular structure. So with this, we have done actually several, and several marmoset brain like this. The marmoset brain is about 3 centimeter in the length, and about 2 centimeter on the width. Okay, and then this is our first step. We show then because the volume of the marmoset brain is about 10 times bigger than mouse brain. Okay, So this is our stepwise approach that we have done the mouse brain mapping, and then now we move to the marmoset, the smallest type of uh, the monkey. And then we actually did some work. We already completed two set of data, two brains of this is a macaque brain. Okay, so this is the raw how the raw image looks like, and then the exact reconstruction is still under process. So because then you can imagine this one projection image, because it's patched, you can still see a very faint division. So each one is probably 10 by 10 or more on the vertical direction of the individual projection image. We patch into one large image and then do every angle this way. Okay. And then thanks for the high brightness, because each small image is the exposure time is less than the 1/10 of a second. So to make this projection image, it doesn't take too long. And so within for this macaque brain, the whole tomography took us just a few hours to complete. And then to compare with that, then we also use a mouse brain. And then, but this mouse brain, we are using even higher resolution. But the end result, you can see it because you know, we expect they're the same, because this higher resolution in this case does not really give you any better, smaller vessel anymore. But the reason we want to try this, because this mouse brain, we are using a higher resolution, which is closer to the resolution required for us to do the neuron, to image the neuron. Okay, so these are some examples. And then we also want to use these well-known more all connected structure to test our tracing algorithm, or develop a tracing algorithm. This algorithm, if you look at closely, all these small dots are either an endpoint of this vessel structure or a branch point. So then by this method, this commercial software, we can identify all these things, except there are a lot of artifacts. For example, in the middle here, it was done by erroneously connection. So it give you this many white lines, which doesn't exist. So that's why we have to develop our own technique. And then now we're trying to use the very popular, say, using the machine learning, and try to do this in a much more effective, more accurate way. Okay, so this is under development. Okay, then the next question is, okay, then why brain? Because the most important brain that we're talking about, the next frontier, and so it's actually not blood vessel. Blood vessel is very important for the medical purpose, because the many doctors told me they believe that every disease is associated with the blood vessel problem. But it's more important is actually to look at the neuron. So, but unfortunately, to look at the neuron of the brain and to map it. So we want to know, for example, if we have a computer, if we want to know its structure, the most effective way is try to draw out its circuitry. So this is the same concept to working on the brain. So even though the individual in the brain, the individual neuron is much more complicated, the function and then there's what it does is much more complicated and than a transistor or even a cluster of transistor. So, but to map its structure, its connection is perhaps the first a step that in order to understand a complete structure. So I make a list here, which is by no means accurate, because but it's in the order magnitude estimation. You can see start from Drosophila to mouse to marmoset to macaque to human. The size is other than Drosophila, from mouse to marmoset to macaque to human is actually approximately 10 times, 1 order of magnitude. So we started with mouse, And then if we move by every time we increase our efficiency, or then we can challenge bigger brains. And then you can see, because the speed is almost directly proportional to its volume, the how long it would take you to complete image this that brain with a fixed resolution. So you can see, and then in terms of human brain, first of all, the volume compared to your resolution is enormous. So, and then by this calculation, we say, okay, the data size of one human brain using, say, 100 nanometer voxel resolution, the data you acquired will be of the order of exabyte. Okay. And then to acquire this extra byte of data, it also will take you very long time. So to map the brain, which is actually if it's not a historical mission, at least it's the first step for historical mission for science and technology, because it's actually fundamentally interesting, because everyone will have would like to know how the brain actually works, because how the brain works is not only a scientific, it's also tied to the entire human culture, or so almost everything we developed is based on how the brain works. Okay, and then then the other important implication is because of the growing problems of the brain disease. And then we believe that the reason that, or not just me, many medical researchers believe the reason we're not able to develop effective treatment or therapy or drug for example, dementia, is because we did not have enough understanding of how the brain works. Okay, so because of this reason, it has a potentially very broad social impact. And then because of the scale of the problem, then by pushing for that, you can almost expect that there will be many technology sort of developed, which could be expected or unexpected. For example, we can already say, for example, in the raw category as well, okay, that will advance our imaging technology. And then more important, we will probably gain some insight of how do we have develop a new computation strategy. And then, for example, then such as artificial intelligence. Okay, the problem is, okay, as I mentioned before in the last few slides, it is an important task, but it has been considered very difficult, if not possible, because at the present, there's almost no technique that you can perform such a task without making a huge compromise. Specifically, to finish this mapping job, as I say, you need to accumulate so much data. And so you need to have a very high speed. Otherwise, you will never be able to finish the job. Okay, and then also you need a very high spatial resolution. Otherwise, you will not be able to resolve the fundamental structures, such as the neuron and its connection. And then that's how we started with this the SYNAP consortium. SYNAP was the short name for, we made it the synchrotron for neuroscience, an Asia-Pacific strategic enterprise. But after we launched it in 2020, we soon realized the interest actually well beyond what we have organized the synchrotron in the Asia-Pacific region. So, and then by organizing this consortium, the mission statement is very simple. To say, okay, it is an effort to image the neural network of a whole human brain, okay, with a proven performance, because we don't want to spend too much time to argue with the biologists and say, oh, okay, whether this technique can reach. If we propose something which is a performance that we need to develop, then the biology community would not believe that. Okay, so we say we are using the proven performance, means almost every synchrotron could do this, okay, in terms of resolution and in terms of the speed. And then using this, then we can argue with them and say, okay, the reason we cannot do that with one synchrotron or one beam time is the amount of the data, amount of the task is too big or so big that we need many other synchrotrons to work together. Okay. So this is our mission, okay, statement. And then it was launched at the 2020, January 15. And then we are saying, okay, at that time, we target to have the first human brain mapped by 2024. And mapping, of course, as I said, okay, I have already talked about this. Okay, and then based on this proven performance that I will list it if you're interested in the future, in later, we calculate using one synchrotron beamline, such as the one we have in Taiwan, would take us probably 30 years to finish a human brain. Okay. So that means we must accelerate because, of course, the obvious choice is let's do a parallel imaging, okay? And then parallel, you can argue, say, okay, why don't you put 10 synchrotron beamline at our synchrotron, and that will do, that will accelerate the task and make it into, instead of 30 years, and make it into 3 years. Of course, and as a long-time synchrotron workers, we knew that was not possible because there's no government agency or grant will invest so much on one project, okay, on putting so many beamlines together or putting the whole synchrotron to those tasks. So we decided this approach of Synapse is actually, in a way, is actually kind of risk sharing because synchrotron has been a multiple user or multiple instrument technique facility. So it's not so much a pressure for a synchrotron to allocate, for example, one beamline, for example, and then to join the thing, and then to advance this technology or advance this science together. And then there are other things we need to develop. So we can say, okay, if we can prepare the sample faster, and then do everything by automation, and then also speed up the data transfer and so on and so on. And then with this, then we can do the Synapse is actually probably the only solution for this task. Okay, so when we started 2020, then we have like 6 synchrotron facilities joined, including Japan, Korea, Shanghai, Taiwan, and then Singapore and Australia synchrotron. Okay, and then our design of this consortium is each synchrotron is coming to join this consortium with a research institute. For example, in my own institute, Academia Sinica, is coupled with our synchrotron. And then so that we need the synchrotron to provide the beamline and then access, but we also need a group of scientists that is able to develop further the technology, the imaging technique, and also to process the data. So this has happened to for example, in Japan, it's the RIKEN and the Spring A Center, and Singapore is National University of Singapore, coupled with their SSLS synchrotron. And then over the years, and it was the inauguration I showed already many years ago. And then most of the synchrotron directors show up to sign this MOU to launch this project, this program. And we even have 3 Nobel Prize to show their support in this meeting. Okay, and then this consortium we will focus on the imaging technique. So X-ray technique is the basis. So we're going to use X-ray technique to build this the circuitry or the road maps or these, and then we would make this as a structure which is able to incorporate all the other technique, such as either functional, molecular technique, which has no capability to look through the whole brain, but given them a good registry. For example, many people made the example to explain this. It's like we are mapping like a Google Earth. We're showing you the continent, showing the interstate highway, and so on. And then the detailed information can be annotated by information obtained from the other technique. So this is one of the important development we kept in mind is when we develop this thing, we want to leave room for our database that allow other technique to put in their information. And then what we offer is that if you look at just any high resolution technique like a TEM, you look at one piece of sample, it'd be very difficult for you to know where exactly it's from, and then what is the relation with the larger part of the brain, for example. So this is the idea that we have about the integrated or incorporate other technique. But X-ray being the only technique that we can look at the whole brain, and then with a sufficient resolution to show at least the major connections. Okay. So through the years, since 2020, which is affected actually very much strongly affected by the COVID because it is an international collaboration project, and then the COVID exactly prohibited that. So, but still with a very tough, because I personally, for example, was quarantined 4 times, and each time is like 2 weeks because of the travel. So through this effort that we are able to sort of standardize and calibrate all the participating synchrotron facility and the beamlines, and set up a station in these synchrotrons. Okay. So, and then at the 2024 into this year, then we are very happy in that we have actually new members like Thailand Synchrotron and then the Sesame in Jordan joined us officially, I think in 2022. And then now in the next month's meeting, Poland Synchrotron Polaris, and then the computational the research institute called SANO will pair together and then come to the meeting in the south of China to sign the MOU to become an official members. And then we are also in contact with Brazil, which show very strong interest to join this consortium. So in this way, we will be soon have at least sort of 10 member countries. And then many of them, for example, in China, now we have 2, and then the third synchrotron is in discussion. And then in Japan, we also expected with the Spring A synchrotron, and then the new synchrotron, the Tohoku synchrotron, might also join the consortium. Okay. So, and then this consortium, continues to take the brain image, mapping the brain. That one of the key objective is through this collaboration, we can develop a new imaging technique. Okay. For example, one of the best example is this one we call it X-ray light sheet microscopy. We give a name, a fancy name as Maxwell. And basically, it was using the very high precision mirror produced by the Spring A synchrotron, and then use it to focus X-ray into one dimension, and then make it in a very thin light sheet. Then the illuminated sample, which has been labeled by the scintillating nanoparticle we developed. These particles are of the size of about 10 nanometers. And then the beam we can focus, the first test we're using 60 nanometer thickness beam, and then scan through the sample. And then those scintillating nanoparticle was only lights up when the X-ray hit it. So then this type of imaging, even with visible light microscopy on top, look at the emissions of these scintillating nanoparticle. it does give you a very, very good Z resolution, which is defined by your light sheets. And then in the XY direction is a typical normal X-ray visible light resolution. But we also borrow the same idea of these super resolution microscopy. And by processing the data, we very recently we achieved actually 7 nanometers of the XY resolution, and then 2 nanometers of the Z resolution. So this is manuscript is finished, is prepared, and so we are in the process of submitting this paper. So that will be the first time you see that we have three-dimensional imaging with resolution all below 10 nanometers in all three directions. So this is one example we show without these super resolution deconvolution. The Z resolution is 65 nanometer. You can see from the image. And then, so this is one of the technique. We believe there'll be a lot of potential being the one sort of complement the full field imaging like the one we are doing for mapping. Okay, and then all these imaging strategy was published. The first publication was in 2017. Okay, so you can check it out. At that time, we outlined how we are going to do this brain mapping. And then more recently, 7 years later or 6 years later, we published another one with much more concrete line of thought and supported by many preliminary data to show that this is a viable roadmap to the large brain. This large brain actually specifically mean that the human brain. Okay. And then again, then come back to the result of that is then we're going to have a lot of data. Okay, so this was this picture was taken at the 2016 the SFM meeting, the largest neuroscience meeting, and in the U.S. And then our partner, Professor Anxin Chang, was giving a presidential lectures. And then he outlined that he announces that we are going to use synchrotron X-ray tomography to do this mapping. And then this paper was a report by Nature, and then showing outlining all these things we mentioned. But the title of this is Big Brain, Big Data. So the data, as I said, if we collect it by X-ray with a 0.3 micron resolution, in all three directions, the amount of data we will collect will be 1 exabyte for one human brain. And remember that I will talk to you later, so okay. But then this is another example because Professor Anxin Chang, that was the one giving the talk, he was an expert of the Drosophila brain. And he spent something like almost more than 10 years to look at over millions of 5 millions, I think he said, Drosophila, taken out one by one and using this tissue clearing fluid that he invented to 2002, and then make the Drosophila brain transparent, and then express the floor for GFP, for example, and then image it by confocal microscopy. And it took him more than 10 years to finish only 50% of the neuron. So then he said, just jokingly, said by this speed, the Drosophila brain has 130,000 neurons, but human brain has 55 billion. So if it takes him 20 years, then it would take 17 million years for him to finish the human brain. And then he was not doing this by one microscope. He has his lab has at that time 10, and then now it's probably 30, 40 confocal microscope and imaging this simultaneously. Okay, for X-ray part, we believe that, as I mentioned to you, we believe we can do it much faster. For example, as I say, 3 years. And then, but the problem is, the most challenging problem is the data. Okay, the single fly brain is already 100 gigabyte. and the mouse brain is hundreds of terabytes. And then we want to map, if we want, because this brain, we are only imaging few percent of the neuron because of the staining method, Golgi stain we use. But if we complete this by the map with, say, 100 brains, then it will become tens of terabytes. And then when we do the human brain, then human brain, the size is already 2,000 times more than the mouse brains, and you calculate. So means, okay, we have to accelerate this, okay? And here I'm showing some examples of that we do, for instance, for the Drosophila brain, and then we are able to stain the neuron without actually sectioning even the skull. So, and you can see by sectioning, we can see inside, this is the Drosophila brain, and all the things we can trace. So I would speed up because it's the end. So the rest is just showing examples. In the last couple of years, what we have done. This, for example, is a mouse brain. This is the first time we try to put the blood vessel, which is the brown, that's a gold features, with neurons, which is the green color features. And then, of course, these are two different brains, but we're sort of trying to merge it together and to show how exactly they're related, or how roughly they're related. And then this is the projection image of these things. And you can see also the blood vessel, which these are straight lines of the blood vessel which is stained by Golgi, not because of our perfusion. So you can see it's not so well connected. And then so this is how it looks by one completely slice. So by this slice, if we take the whole brain, then we can do by the whole brain without cutting. Okay. And then these are the high resolution image. So I will conclude. So it's almost 1 hour with my my talk. And then after this, I will play this movie when I was waiting for your answer. Okay, the progress of this consortium is after many years, after 4 years since inauguration, we are finally able already to take on the human brain. So we expected the first donation of the brain will arrive hopefully at the end of this year. But right now we do not have the speed to image the whole brain at once. Okay, so we are still waiting for few developments. Once these development installed, we project that we can image the whole brain within a few months. Okay, but before that, we would try to look at a few specific region. For example, if we think we can spend just instead of months, we can just take 1 or 2 weeks of beam time, when we can map out the complete hippocampus region, for example. And that will be actually already quite significant, because that will be the first such a comprehensive mapping of any significant brain regions. Okay, then I would not discuss. I would just show you, besides other than the technology, the imaging, and then the biological data from the brain, and then this connectome map, there are many other possible technology impact. For example, the imaging, as I mentioned, and also the new imaging technique that we developed due to this process. And then we can do in the future, for instance, spectral microscopy coupled in with elemental chemical mapping, and then so on. And then, but most interesting thing is actually the neuromorphic computing. This is not very mature yet, because I think most of people still have no idea how we can learn from the human brain to make a better computer. And the more neuromorphic computing is the one coming closer to mimic how the brain works. Okay, so I just list a few things I gather. For example, the first neuromorphic computer was actually built by IBM, and then the first computer was actually sold to American Air Force. Okay, and I have no idea how it's useful or what it does better than than the regular silicon-based computer. It's different than quantum computing. Quantum computing, people actually know quite well what it can do best, and then of course it's not everything. Okay. So, and then, for example, we just recently sent out the proposal to the Chinese government, and which is pushing for this AI for science project. And then within this project, we're asking a group of computer scientists to help us to develop the necessary algorithm or computation tool to handle our data. The first task, for example, when trying to do a sparse projection reconstruction, means that instead of using filter back projection, which require hundreds, if not thousands, of projection to do the reconstruction, and then hopefully by machine learning, we can do with much fewer projection, which is not only increase the imaging taking time. For example, if we can do, which we have already demonstrated that this reconstruction can be done with 20 or 30 projection, and our goal is push it to under 10 projection. And then compared to 1,000 projection, the acquisition time is literally 2 orders of magnitude faster. Okay. So that if you just calculate this way, that means instead of taking 80 days to finish a human brain, then it could possible that we can do it within few days. Okay, and then how do we extract the wire diagram, which is the information we need? And then from these exabyte of image data, then what can we extract these connection information? Okay. All right, so I think I will stop here, but by showing a few images or movies when I go to the very end. Okay. So here I will conclude because we modified that. So because this Synapse project is really restarted after the Synapse after COVID pandemic, but within the last few years, within the years during the COVID, instead of pushing for the large scale mapping, we focus on develop the technology. So now we are very confident now when we started with all the investment on the hardware and the computation, we'll be able to finish the first brain mapping before 2026. Okay, in 3 years. And then I will have this sort of a joking slide. It's okay. There's an old saying that go fast, or if you want to go fast, go alone. If you want to go far with friends. Here we want to go fast in terms of it means the imaging, and want to go very far to reach the human brain. And then we are gonna go with all these friends that have been collaborating with me and helping this project. Thank you very much.
Oh, thank you. That's a very fascinating talk. Are there any questions for the speaker?
Okay. Oh, sorry. Okay. Yes.
You can either unmute yourself and ask, or do the raise your hand thing,
Okay.
like I just did there.
Okay.
Well, let me ask a few questions if I can.
Yes. Mm-hmm.
Is it possible to get the resolution at a wavelength where you could probably get some chemical signatures of the neuron on a spatial basis? So is like doing this in the IR.
Yeah.
Does the wavelength mean that you can't get the spatial resolution? Would that be a deal breaker there?
Actually we have of course these kind of idea they always come up and then within some discussion, but to be honest, that we have actually no idea how we can implement that, for example. And then being an experimentalist, and then dealing with a large facility, then actually we have been all educated to reduce your ambition to these things. Okay.
Yeah.
So for example, that's why I said the Synapse was proposed with a very in terms of really front end technology is very conservative because all this parameter I show you is very conservative. So, but that doesn't prevent us, for example, all these consortium, because right now, for example, we are already setting up a few beamlines because we have developed the technique during the last few years. So once it's implemented, it could be so fast. So we actually do not require that to separate the brain, one human brain, as we proposed the very beginning of Synapse, to different facility, and then everyone collected the data, and then finally we put the data together into one place and do the process, and then make a database of these wire diagrams so that can be shared by everyone else. So because of the COVID, that we are forced to do the work at home, so we decided, okay, we will try to increase the performance instead of doing the mapping. Okay, so the advantage of that is that get us to learn another approach, strategy is when we are talking about all these facility, then I ask all these scientists, because they all understand once they join this project, very soon they'll be doing extremely boring job, because most of the job is actually sort of can be replaced by robot or by AI. So what I encourage them instead is, let's try to develop your own idea and how can we improve the speed, how can we add a new information such as the one you proposed. So can we use X-ray or in a different, I was even thinking about, can we use the modulation of the wavelengths for something like that. For example, because you want X-ray to be penetrating, can you modulate the wavelength to give you something to excite, for example, the vibration spectroscopy. So these are the things. So I think we just request asking for our partners to work on this, because in the future, I think once we finish the first brain, because this first brain is likely to be completed in China, because it'll be probably a Chinese donation. The donor is probably Chinese, and then the China or almost every government does not allow you to transport the human tissue to other country. So if we have that, we most likely will be doing with a few synchrotron in China. But then at the same time, we can use this because to complete a map, we need hundreds of a brain. Okay. Of course, each is not like you have to wait for 100 brain to complete a map before it's useful. In every step, even if we image a very small region, because these are the information never being seen, known to be a medical or neuroscience community. So they will be, without a question, will be very useful. So this will allow us to say, okay, each synchrotron, for example, if the African synchrotron is ready, then you can acquire your own brain, and then with one beamline, and then you can do probably 10, 20 brains a year, and in automatic fashion. And this data will be collected in the future, being a commitment to be this consortium to put together. And then this final database, we promise, will be shared by the world. Okay. So but at the same time, that will allow each synchrotron to look at, for example, any specific disease that is interest most to your country, for example. You have a high population with this specific disease, and then you can image at the same time the healthier brain, which is donated due to private car accidents or whatever. And at the same time, you can also collect information from this diseased brain. Okay, and then slowly we can put together a very complete map. And then at the same time, that you can also encourage your local medical community or something to use this not completed yet connectome map, and to do their research to get new findings. Okay, so that's my very long answer to your short questions.
Okay.
Yes.
Any other questions? Trevor, did you have a question? I see you unmuted yourself.
No, I didn't really have a question, but I thought it was an extremely interesting talk. And is the camera that you were using, the advanced cameras that you're using, they're all in China, are they?
No, the Chinese synchrotron, Beijing synchrotron has a project and trying to make it's not actually advanced. For me, I was joking to these are good friends. I was joking. No, they're just making a bigger Russell number pixel. So the next version they are going to be rolled out is probably 6K by 6K. But I told them, if you leave it to the industry, the commercial industry, it'd be much faster, which is the approach the Spring A, for example, took. I'm actually now talking to you from Spring A. I was in the Beamtime experiment with my team, and then this is the last day of our Beamtime. So, and then I knew that they actually collaborate with Sony to make their detector for free electron laser, and then also for this. And then I think that's also a very effective approach. But I think China does this for a specific reason because they do not want to leave a stone unturned. They want to make sure they have all the possible technology to prepare for a scientific sanctioned war. So I think so. This camera, from my own understanding, there's really nothing really advanced of they have developed this high pixel number camera for the photon counting device, but that's not really necessary for our X-ray imaging. That's more for like a diffraction imaging or something like that. So I think the camera is not really an issue. I think even without waiting for too long, we will find a camera with 10K by 10K pixel numbers. The problem is it'd be more difficult to make it. They call it a scientific grade. But again, I do not believe that is very important or essential. Okay. So anyone with a probably reasonable technique or some, you can buy the commercial chip and try to make a CCD yourself. That's within not only that doesn't even require a consortium work, but probably any facility, and then you can find that 2, 3 scientists can already do this job. All right.
Thank you.
Thank you.
Leo, did you have a question? I see that you have.
Yes, Lawrence, model question is a comment, if you allow me. First of all, let me introduce me to the speaker. I am one of the people behind a project of a new synchrotron in the Caribbean region.
Yeah, I was told by. Yeah.
Okay, so and we are in the strict contact with the colleagues of the African Light Source. Now, your talk was very interesting and stimulating, but of course, to some extent, made me think, well, this guy is presenting us dreams which for our regions are out of scope. But instead, I would say I would like to comment how one can make this project also interesting for regions where we are not in condition of participating in an active way to your research. You mentioned a certain interaction with medical community. And medical community often in Africa and in Caribbean is strong. We are thinking to have a synchrotron built in 5 years, 10 years from now. But for example, there is all a work of computing which can be very useful for this type of research. So my question is, would not you think that a project as large as your project cannot have also a component of dissemination among the young people to try to build an expertise of few people who can be the core from which in 10 years from now, this type of research is feasible in Africa and in the greater Caribbean?
Yeah, thank you very much for the question. And to be honest, okay, I think we would like very much to think along your way, but unfortunately, but indeed is not what I originally planned. Okay, because my less ambitious plan is actually try to call up these few synchrotrons, which are many good friends that I get acquainted or develop a very good friendship over my career. So I said, if I can convince them, say this is something worthy to do, and then everyone just give a certain percentage of their energy, then we can do this job together. But then over these years, with more and more people, and then yes, indeed, we will have to go to this direction, as you mentioned, because that's why I was actually our board. We have this Synapse, we have a executive board, which is, in a way, it's the operating body of this, which is consists of each country will have a one membership, and then in this board, and then we can discuss and decide things together. So we decided very early on that, first of all, we will not discriminate against any facility. So when we do this, when you have already a synchrotron, for example, like the Singapore synchrotron, which is not at least in the same performance level as the rest, like the Spring 8. But we decided it's more important to have the spirit of a large synchrotron community and the spirit of working together. And then so that's why my title is, cross the border or borderless approach. So we do not want, because we do not like to see what the scientific border now is actually constructed. So this is also the same idea of Professor Moving Pool. So he wants to make a even larger consortium just for the brain mapping. So that will include all the different techniques. And he has the intention to make this into a consortium like, if you know CERN. He said that we will make all the facility open to each other, and then collect the data, and then the data is also open to everyone. Okay. So I think this is, so then we have to then come to think about, for example, that's how we practice, and it's quite successful. For instance, after the first membership, then we say, okay, we approached Jordan. First of all, it's like your case here, is we ask you if you're interested, okay, if you're interested, and then we will talk, okay. If you're interested, you think, okay, then we will try to find something that the community, if the synchrotron is not even built, that can contribute to this grand challenge, okay. So that's our commitment, and then we promise that it will be happen. So if once you show, and then I think the whole board will work as one community, then we'll try to help in any way. First of all, if it's okay to increase the interaction between the medical community and the synchrotron facility, which is also very important, not just in the African synchrotron or Caribbean synchrotron, but every synchrotron. But that is exactly what we did. And then our experience can be translated, if not completed, borrowed, can be translated with the help of the local scientists. So I think this is the good thing is that we have a big enough objectives. This objective is so big, so I think can be shared by everyone, and then it cannot be achieved by a single facility or even single country. So you don't need to feel, shy about, for example, Thailand synchrotron. Okay, of course, this is the first generation synchrotron. The performance is reasonable. We can still appreciate the access. But on the other hand, they are building a new synchrotron, which is on the 2030, if they expect to finish at 2030. So we don't ask a question, say, oh, it's if you are finished in 2030, then it has no use for us. No, the idea, taking the data is one thing. Taking the one human brain data can probably be with our speed that we recently demonstrated, can probably be done by one single beamline at the time of like 2 months. So really to collect this one set of data, it doesn't require anymore all the synchrotron. But we want the synchrotron to work together to see, okay, how can we then move to the next step? That we want to collect 100 brain or 200 brain data. So in the future, it will be like donating the cadaver. For instance, China is already in the process that they have already 3 big brain banks. So asking for the patient to donate their brain is become without any legal obstacle. So just like you donate your organ for transplant, now they ask you also, do you want to donate your brain? And they have the largest hospital in Beijing actually have this brain bank. They are very efficient, and then they are taking care of all the process. So I think the essence of this is actually try to find a new way to do the image, putting new information, more information. But the most important thing I would like to have this community to work together is actually find a new application. Frankly, even if we constructed the first connectome map, the map from one human, we have frankly no idea how it can be used. So this requires our interaction with the medical or biology community as early as possible so that they can start growing with us and then find out if we have this map, what they can do to their research or to advance the medicine. All right, I hope does that answer.
Yes, but I would like, if you allow me, to make a final short comment, very short.
Yeah.
Because, of course, our project is a project for the future. But I noticed that among the possible collaborators of yours is Sirius. And we are in strict contact with Sirius, which is supporting our project first. And second, I've seen among the authors of the paper on the physics reports you mentioned, the last one, because we have so many. My eye fell on the last one. Margaritondo is one of the most active person in our group. So that I think that a possibility of establishing the discussion to see what can be done in this direction, small steps perhaps could be considered.
Sure. Okay. Yeah. Professor Margaritondo actually is the chairman of our executive board. Okay. And then we take him as actually because at that time we want to have this executive board with someone so like that it's possible to adjudicate it in case of, So we ask Margaritondo Giorgio as the chairman, which does not represent any member country because he's now in Switzerland. It does so. And then if you're talking about anything you want to be, and then I am now assigned to the job of CEO is exactly the one to talk. So if you want me to help you to organize something, and then I will be sort of at your service. Okay. And in fact, I'm going to do a early retire from my job in Taiwan, and then I will be serving this consortium full time.
Thank you.
Yeah, just okay. Draw me a note if you think there's any idea. I think it's not just. I'll be happy to do that. This is what my duty of being assigned by the Synapse.
If you can write your email in the chat, I'll be happy to take note.
I'll make sure you
Okay.
get it, Leo.
Okay,
Okay.
great,
Yes.
Laurie.
Let me ask just a quick question. Hopefully, maybe
Yes. Yes.
is I didn't notice that the Shanghai soft free electron laser as your one of your consortium members. Does the high intensity of a soft X-ray XFEL lend towards the greater speed at data collection, do you think?
Oh
Or is that
no.
too
No,
bright
I
to fry
no
the to
no.
fry the brain?
Actually, we have no idea. We have not thought about. Actually, I just before the talk, I actually removed few introduction of the three electron laser because I cannot see in the near future that we will make use of that. Even though this laser is next door, and then we know almost everyone that direct, but they did in as a facility they did not participate the synapse yet. So this will be mainly the synchrotron work, at least for the first phase. As after we build the road map, okay, of
Yeah.
course, the free electron laser could probably in the future give us for instance, molecular sensitivity to identify whatever protein is and where and so on. But that is not what we concerning right now.
Gotcha. Okay. And then I guess one comment, I mean, you do one brain, but
Yeah.
there's got to be some brain heterogeneity in a global population. So you probably have to be
Yeah.
doing a whole bunch of brains before you really
Yes.
learn
Yes.
anything
Yes.
biologically interesting.
Yes. Exactly.
So,
Yeah.
well, if there's no
So
further
that's why.
questions, oh, go ahead. I'm sorry. Go ahead.
So that's why we are not. That's what I said. Okay. We said the first one brain is just sort of like symbolically, you
Yeah.
know, said it's really to make it's much bigger than I make the one brain already sounds very challenging because the data side, but then think about then to have this reasonable map, at least we need something 100 because of the Golgi staying 3% to 5% at most of the neuron. So you see, okay, even by if they are completely random to build a map, how many do you need? Even in a statistical sense, you probably an order of 100 of them, and then
Right.
there's no way one facility can do. Okay, and then that's
Yeah.
good actually. Then that allows, for example, that you can look at the African local populations, and then something like that, then the data will be much more diversified, and then will be much
Right.
more interesting. Yes.
Yeah. And then so I guess at each lights there's a sort of a standard protocol for collecting the images and the standard workflow and protocol.
Yeah. It's
So that's
it's not.
something that we probably need to talk about in terms of
Yes.
training.
Yes. Yes. And then of course we hope because at the beginning we are inherited this few beamlines. That's what the work our group did in the last few years. That we went there, and then with their help to implement the hardware, and then implement the software, so that we can take the data with a very similar quality. Because original idea is we want to have a one brain taken into several pieces, right? So when get to that, then we have to make sure the data quality is good enough. For example, that you have to maintain the same resolution so that we can put the data together, you know.
Yeah.
So and then but then we compromises, okay, we calibrate, for example, this beamline because okay, like Singapore is lower energy. So in order to get to this we need to use a wide beam and so on. And then the speed will be very different. Okay,
Yeah.
different beamline. So this way we can calculate, say, okay, then maybe we don't give you such a big piece because then it will be behind. Then we'll give you a smaller piece. But our agreement is we don't, discriminate people, but how much we're gonna work together. Then we don't tell, okay, oh, your facility only contribute 2%. So in the credit line, we would say, okay, no, we're not going to do that. Okay.
Right. So
Yes.
this is a little bit to Leo's point. This is actually a situation where, well, every little bit helps, and it
Yeah. And
actually
then,
it's almost an advantage that only a few facilities will
Mm.
do the work because you need a very tight quality control on the methodology.
Yes.
If that makes if
But-
that I mean
Yeah,
maybe
but
that makes
that's
sense, maybe that doesn't.
but that's reasonably technical because
Yeah.
I was helping Shanghai Synchrotron to build a program to install the brain mapping in the synchrotron. So
Yeah.
in this proposal, I already tell them, okay, I want you to take the responsibility because with the funding to support the newcomers. For example, for those synchrotron like yours, you're building, and then many synchrotron during their construction phase, one of the typical practices they send the scientists outside to work. So I said, okay, if you agree to do this, then you should think seriously, allocate resources to accommodate this visitors or young scientists coming to work with you, not necessarily to learn, but also to contribute.
Yeah.
Because when they come in, then there be valuable manpower, and then they can acquire the experience, and then probably even before the synchrotron is built, they can already engage with their local scientific community to think about how they can use this data.
Yeah. Yeah.
Yeah, that's definitely we have the plan, and we're totally willing to do this.
Okay.
Yeah.
All right. Well, if there's no further questions for the speaker,
Yes.
I will conclude the session by just saying thank you,
Yeah. You're
and
welcome.
that I'll continue to be in touch with you because I've
Yes.
written down a bunch of ideas
Yes.
that
Yes. Great.
both in terms of working together and then my own sort of scientific curiosities.
Yes.
I'm curious about this XFEL
Yeah.
business because
Oh, okay. Yes.
I don't know if it's sort of too intense to sort of you destroy before you image, like in protein crystallography to say
Yeah, yes,
destroy before diffract
yes,
before destroy. So,
yes. But yes, we actually I did work on free electron laser for on and off for several years with in the spring age. We have actually published a few things. So I know exactly what its limitation and what its capability.
mhm.
Yeah, so just okay, so you're welcome to discuss for idea. We can even ask for example, the spring A scientists to collaborate.
Sure.
Okay, so this is the idea. So we don't, we just want people to participate. We do not really need to discriminate whether you can bring in anything. Okay.
Absolutely.
Yes.
Okay.
Great. All right.
Well, thank you for your
Well,
time and thank you everyone for
yeah.
attending.
Thank you very much for being in the talk. All right.
Okay.
Okay. For me,
Alrighty.
it's good night. So
Okay.
I
Hey,
see
good
you.
night. And
Yeah.
for
Thank
everyone else,
you.
good evening. And for
All
myself, I
right.
guess it'll be good afternoon.
Okay.
Okay. Talk to
So,
everyone later. Thank you.
all right. Bye.
Bye.
Thanks, Lawrence.
Okay. All right.